All right, folks, this is going to be the review for 16-2 enthalpy calculation. So remember we discussed a little bit about enthalpy itself and just the fact that enthalpy is related to energy. Okay, and in this case, when we look at enthalpy, enthalpy is signified by H. And our real big focus here is actually calculating delta H. That is the change in enthalpy in a reaction. We know that if delta H is positive, that it is endothermic. And if it is negative, then it is exothermic. Okay? And we also discussed 3 different ways that we can do this. The first one we're going to look at is enthalpy of formation, which is just the enthalpy value for each individual compound. From this, we can then do some math in order to be able to figure out the delta H for the reaction, and therefore would be able to know if it is endo or exothermic. The formula for this is the sum of the delta H of your products minus the sum of the delta H of your reactants. Okay. Things we do need to keep in mind are coefficients of our equation, because we will have to multiply those in order to get the correct enthalpies. Okay. So moving down here, let's look at some practice problems. And for the first one here, we're going to be asked to calculate the reaction enthalpy for the combustion of propane. So the first thing we need to do is write our equation. So C3, H8 plus O2 yields CO2 and H2O. So again, we need to go back and balance this. 3 and 6, like that. And again, it's just products minus reactants. So we're going to get water here, which is negative 285.8. Now remember, because that is it has a 4 as a coefficient, we need to multiply that by 4. CO2, we're going to multiply by 3. And we're going to subtract it from our reactants. Now, oxygen is 0, so we don't need to include it. And we're going to subtract negative 103.9. Okay. And we just plug those into our calculator and solve. So what we get here at the end is negative 2,219 kilojoules per mole. Okay, and again, that is delta H of the reaction. So that tells us a lot about this reaction. If you think about it, combustion of propane, combustion reactions release a lot of heat, right? So you would expect this to be a negative value because of how much heat is released in a reaction of propane. You know, you use propane all the time for your grills. All right, for the last time this year, I'm Hank Hill, and I sell propane and propane accessories. Oh! 40 years in the future, when people are watching this YouTube video, probably long after I'm dead, people are going to wonder what's going on. YouTube probably won't even be a thing. It'll be something else like, I don't know, 3D tube, where you've got 3-dimensional people, and I'll pop up, and I'm just going to shut up. Next one is bond enthalpy. Okay, bond enthalpy just takes the enthalpy that's present in, well, you guessed it, each bond. And then from that information, we can figure out the enthalpy of the reaction. So there's 2 things that are critical here. This one is a little bit different. This is reactant minus product. So it is different than the previous one, okay? Really important to remember. Reactant minus product. And then we also need to consider the Lewis structure, because a lot of times we cannot tell if a bond is single bond or double bond. You see here you've got lots of different enthalpies for multiple bonds, so we need to know if it's single or double before we go through and do our enthalpy calculations. You don't have to memorize any of these numbers. Everything will always be given to you, so it makes it nice and easy to kind of go through and figure out. So let's just do this first one here, combustion of methane. So we'll just do this first one here because I think this is pretty straightforward once you know how to do it. And again, combustion reactions, you should know how to write those out. Yada yada yada, all that good stuff. So 1, 2, 2. Okay. Now I'm going to scroll back up a little bit because I cannot see my enthalpies. Actually, I may just do this problem up here so we can see it really, a little bit better. So again, what's important here is we need to know what type of bonds are present. So it's really important that we write out the Lewis structure for each of these. And to do it correctly, in order to correctly get what type of bonds we need. Okay. So erase those lines. We don't need them anymore. And now let's see what we do here. So here I have 4 carbon-hydrogen single bonds. So I need to, I'm just going to scroll back up here. So here I have 4 carbon-hydrogen single bonds. Okay. So that's going to be 4 times 413 plus we had 2 O2s, remember that? And we also had 2 water molecules, so we will need to keep that in mind. Oxygen-oxygen double bond is 495. But remember, I had a coefficient of 2, right? So I need to keep that into consideration as well. So not only do you need to consider the number of bonds, but you also need to consider the fact that the coefficients of the equations play a role in this as well. We're going to subtract 2 times whatever the carbon-oxygen double bond is, 1072. And again, it's the sum of these. So I need 4 hydrogen oxygen bonds, because again, that coefficient of 2 there. And that is 463. So same concept here. We just plug that into our calculator and we solve. What we get here is our delta H of our reaction is negative 1,354 kilojoules per mole. Okay. So again, it's the same concept here. We do need to consider the number of bonds as well as the coefficients of our equation. All right, let's move on to the very last thing for this particular unit. They see me scrolling right down. Okay, so here we're going to talk a little about Hess's law. Now, Hess's law, basically, we need to combine simple equations into complex ones. And then what we do is we take the sum of our H values, and that tells us what the delta H of the reaction is. So there's a couple things that we can do here. You can flip a reaction. I don't know why flip doesn't have any in it, Joe. But keep in mind that that's going to change your sign. Okay, so if I need to flip, let's say I need to flip this first one here. If I did, then it's going to be a positive value rather than a negative value. And the other thing too is I can multiply equations by values in order to get them to be the same values as what's up above. If I do that, I need to multiply my delta H by whatever I multiply that by, okay? So again, it's just about figuring out ways to combine things together. Remember that things on opposite sides can cancel. So let's take a look at this equation down here for number 1 and see if we can figure this out. So the first one, B2H6 plus 6Cl2 yields, sorry, the air didn't show up there, 2BCl3 and 6HCl. So the first thing I'm going to look at here, I have B2H6 on this side, and I have it on this side here. So I'm probably going to actually leave that as is. So I'm going to go ahead and write that with a different one, different pen here. So yeah, B2H6 plus 6H2O yields 2H3BO3 and 6H2. Okay. So we're going to go ahead and leave that one as is. Now let's take a look at something else. I need Cl. I need 6 Cl's on the left side here. So I'm going to draw some arrows here so you guys can get a better idea of where the reactants and products stop. So if I look here, I need 6 Cl's on my left side. Well, here I have a half of one. So in order to get this to work, I'm actually have to multiply this whole thing by 12. Okay? But again, if I multiply that by 12, what I get is I get 6 H2s plus 6 Cl2s yields 12 HCl. Okay? So far so good. And then the last thing I'm looking at here is I need BCl3 on the right side. But here I have it on the left side. So if I flip this, and I also need 2 of them. I forgot to take that into consideration. So what I'm going to do here is I'm going to multiply this by 2 to get 2 BCl3, and then I'm also going to flip this one. Okay? So we need to multiply everything by 2, so in flip it, we're going to have 6 HCl plus 2 H3 BO3 yields 6 H2O and 2 BCl3. Okay? Now we need to look and see if everything cancels. If it does, then we can go through and add our delta H's together, whatever those are going to end up being. Okay? So let's go ahead and see what we have here. I'm going to use green for this. So what's going to cancel? Well, my H2Os are going to cancel, right? Because it's 6 and 6. My 2H3BO3 is going to cancel. My 6H2s are going to cancel. Everything else is good. I've got 6 HCl here and 12 here, so this will cancel, and this is just going to leave this as 6. So if I finish up, I have B2H6 plus 6Cl2 yields 2 BCl3 and 6 HCl, which is good because that's exactly what we want up there. So now we just need to go back and look at what we did for our equation and then add those delta H's together. So the first one here, we didn't do anything to that. So we're going to leave that as negative 493.4. The one at the bottom, we multiplied by 12. So we need to take 12 times negative 92.3. And then the last one we flipped, so it's going to be positive 112.5, and we multiplied it by 2. So when we get all of those things figured out and taken care of, we can then add all of those together, and that will give us the delta H, or the enthalpy change for the entire reaction. So for this entire reaction here, my delta H is negative 1,376 kilojoules per mole. Okay. So again, the concepts here are pretty straightforward. We need to be able to combine those equations together in some way, shape, or form to give us the total equation up at the top. And so in order to do that, we need to flip equations, we need to multiply them by things. It really is a puzzle, okay? But the more you practice with it, the easier it is to solve the puzzle. I think this pretty much covers what we're going to look for here. I'm not going to do the other practice problems. You're more than welcome to, and ask me if you have questions later. But that's all I have for you guys for today. So I appreciate your time. We will talk to you later, and hopefully you've learned about the 3 different ways to calculate change of enthalpy in a chemical reaction. See you guys later. Have a great day, guys. Bye-bye.